Not very far from Trieste, on the Carso in Basovizza, is the Elettra Laboratory. It was built to produce an exceptionally bright light, synchrotron radiation, a tool that enables researchers to detect structural details of materials otherwise invisible. This tool has many applications in different fields. Let's have a look at the source of this light with such exceptional features. Everything starts in the LINAC, the Electra Linear Accelerator. An electron source is located at the beginning of the long LINAC tunnel. Here, charged particles are emitted by a metal electrode using a principle similar to that which operates in the cathode ray tube of a standard television set. The electrons are guided inside a high vacuum thin steel tube and accelerated up to an energy of 1 billion electrovolts, 100,000 times greater than in an ordinary TV set. The electrons are shot like cannonballs from the LINAC into the transfer line. And finally injected into the storage ring. Here they will circle for 48 hours without interruption at a speed close to the speed of light, with their energy remaining constant. In this amount of time, they will cover a distance equivalent to 4 times the diameter of the solar system. The storage ring is where synchrotron light is generated. It is not really circular as the name implies. It is in fact an alternation of straight and curved sections. In each curved section, a powerful magnet guides the electrons, forcing them to deviate from their path. Each time they deviate, the electrons emit energy in the form of light. The continued spinning around of the electrons produces beams of light which are conveyed into the beam lines tangent to the storage ring. This is where the experiments are performed. Today, Electra has 23 different operating beam lines, each specialized in the kinds of measurements employed and materials studied. The applications range widely from chemistry to biology, electronics, environmental science, materials engineering, medicine, nanotechnology, and archaeology. For example, the X-ray diffraction beamline allows us to study the structure of viruses and proteins by locating their atoms in space. Like all the other beamlines, the X-ray diffraction station includes various optical devices that select the needed wavelength and terminates with the experimental chamber where the sample to be analyzed is located. The light, X-rays in this case, passes through the sample, e.g. a protein, interacting with it in a particular way according to the position of the atoms in the sample. This phenomenon is called diffraction. The diffracted X-rays form an image that can be seen by the means of a suitable detector. This image contains all the sample's structural information. Using a particular software based on the principles of physics and mathematics, the researchers are then able to uncover the three-dimensional structure of the protein atom by atom. One of the applications is the design of new drugs. In order to extend the scientific possibilities of the laboratory, a new light source is under construction next to the storage ring. It is a free electron laser which will be called Fermi. This light source will have unique features. It will be able to produce very intense and short flashes of light of incomparable purity in the color interval between ultraviolet and X-rays. It will be built inside a long tunnel that is itself an extension of the LINAC tunnel, the linear accelerator that supplies Electra. There, electron bunches forced by magnetic fields into an oscillatory path will be stimulated to emit light. In the second section, experiments complementary to those of Electra will be carried out with this light. Fermi will allow researchers to uncover the dynamic behavior of matter, for example by following the evolution of a chemical reaction through a series of ultra-fast sequential shots.